Well, that's just a great call. Timing is everything for time. All right, this is a quick optimization problem for optimizing the building of a storage shed, shape of a box with a square base and a closed top. Let's start there with the picture. Square base and a closed top. Here would be our base, and then a top, something like this. There we go. And then let's move that down so we can have a little more room. Here we go. And it's a square base. So normally our dimensions would be length, width, and height, but here the length and the width are the same. So you could both call them L and L or X and X like this. X, X, you could call them W and W. Doesn't really matter, but it's a square base. So you know that the sides of the base are the same. What else do we know? We know, let's see. So storage shed, shape of a box, square base, closed top. So there is surface on the top. There's surface on the base. And then we have these sides, this side, the back, side on the right, and then the side in the front. And we have a fixed volume of 100 cubic meters. We're supposed to find the dimensions that minimize the surface area. So language around minimize a particular thing, that's telling us we're going to optimize the surface area. Surface area is going to be our objective equation. Anything else, like fixed volume being 100, that has to be a relating equation. So let's see, volume. Here, let's write relating equation. Relating equation. This is also called a constraint equation. That's volume equals 100. Volume equals 100. Volume in our picture is W times H. That's 100. And so W squared H is equal to 100. And we'll use that in a little bit to put our objective equation in terms of one variable. So objective equation is an equation that we want to minimize. And in this case, again, surface area, we want to minimize that. So we want to write an objective equation for surface area. Surface area is area, all right, area of the base plus area of the top plus area. In this case, let's see, the sides all have the same area to them. So the area of the base is W squared. Area of the top is also W squared. Then the area of the sides, each side is W times H, and there are 4 of them. There's the front side again, that's 1, right side is 2, back side is 3, left side is 4. So 4 WH. And again, denominator, not the denominator, the base has area WW or W squared, and so does the top. It has dimension W and W, so area W squared. Our surface area then is 2W squared plus 4WH. And the idea, since we're going to, let's see, optimize this equation through critical points, etc., we want to put our objective equation in terms of one variable. You can put that in terms of W. You could put it in terms of H. We already have a lot of W's, more W's than H's. So let's rewrite H in terms of W. We would have 2W squared plus 4W, and then H, if you go back to our relating equation, we can solve for H. And that's what the relating equation is good for. It puts your connection between your two variables. We'd have 100 over W squared. And then let's put that in for H. This H here is going to be 100 over W squared. 100 over W squared. And we should simplify this. This will be 2W squared plus 400 over W. Here is our surface area equation in terms of W. This is our objective equation. Our next step is going to be to put a domain with this, a workable domain, and then to optimize the equation. So far, let's stop here though. Objective equation, 2w squared plus 400 over w. Relating equation, 100 over w squared. Okay, now to optimize. Let's see. You know what? I'm going to go to the next page. Let's do that. First, find a domain. We're going to need a domain for our objective equation, surface area, so that we could decide on critical points. So in our picture, we have a fixed volume, and then we have to ask ourselves, what are our options for W? What are our options for H? They're all side links, so all of our side links have to be bigger than 0, or else we don't have a picture. And in our surface area here, we just want to write a domain for W, since our surface area equation is in terms of W. So let's see. We know W has to be bigger than 0. W can't be 0 because it's in the denominator. So we would need W to be bigger than 0. Let's see, surface area W. We have 2w squared plus 400 W. Domain for W is that W has to be bigger than 0. It cannot be equal to 0. Again, can't be equal to 0 because W is in the denominator. That would put 0 in the denominator. That's not good. That'd make your surface area undefined. So we have W bigger than 0. We could also write it as 0 to infinity for our domain. All right. Then that's it. There's no upper restriction for W. If W, W were a billion and this is a billion, it's possible that the H is small enough. There's a number small enough that we could take W, a billion times some super small number and still get 100. So there's no upper restriction on W. So now to find critical points, find critical points. And what are we trying to do, just to remind ourselves? If we go back, find the dimensions that minimize surface area. Minimize surface area, we're trying to find a small value, to minimize surface area. This will happen at a critical point. And wherever that critical point is, if we're trying to minimize surface area, then that critical point is going to be the location of a local minimum to be able to minimize surface area. And I guess in this case, the picture, it'll give us a absolute minimum on that interval. So find a critical point, take the derivative. That's going to be 4w minus 400 over w squared. W squared. And let's see, for your critical points, you figure out where your surface area doesn't exist. This exists for all W in 0 to infinity. The other way is to figure out where your derivative is 0. So let's see, let's add 400 W squared to the left side, 400 over, rather, W squared is 4W. Then 100 is equal to W cubed. You can take the cube root. W is cube root of 100. There is our critical point of our surface area. One, it makes your derivative, this will make your derivative 0, plus it's in your domain of our function. Okay, so that is the location where our minimum surface area will be achieved. Let's see, I think you need to justify this. Justify y minimum surface area is achieved, or why does it happen at w equals 3 root 100. You could do that with a first derivative test or a second derivative test. Second derivative, I think, is easier. So if you look at second derivative of w, this will be the derivative with respect to w of 4w minus 400 over w squared. If we take our derivative, this is 4. It's going to be plus 800 over w cubed. And this is positive on 0 to infinity. What does that tell you? This tells us that surface area is concave up on 0 to infinity. And let's see, W equals, let me say this, surface area at that critical point, cube root of 100 must be an absolute min. It gives us an absolute min because, again, our interval is 0 to 100. We only had one location where our derivative was 0, where our tangent line is horizontal. And if that's the only one, and our second derivative is positive, telling us our surface area is concave up the whole interval, then this is the only low value, the absolute min. And then the last is to answer your question. Answer a question. And maybe we did, I can't remember, let's go back. So answer the question. It was find dimensions that minimize surface area. So we knew that our dimensions are W and H. We found W, now for H, and H is 100 over W squared. So let's go back to the bottom. W equals cube root of 100. H is what we need. And what did we say? H was 100 over W squared. So H equals 100 over cube root of 100 squared. I guess we could stop there. We could also write this as 100 over 100 to the 2/3. And if we subtract, this is 100 to the 3/3 minus 2/3, and we get cube root of 100. Then I think that's it. I'm going to pause a second and then just check and then come back. Yeah, for sure. I'm confused, or not confused, convinced that this would work. Just thinking of another way to communicate what's going on. If we have 100 over W squared, another way to write 100 is cube root of 100 times cube root of 100 times cube root of 100, and then all divided by W squared, and that was 2 cube root 100s, and you could cancel this one, this one, this one, this one. It leaves you with one of them, or just cube root of 100. These were meters, so M for meters, cube root 100 meters. So our box, if we go back, what shape actually does minimize the amount of surface area? It would be where the width and the height are all the same. This would be just to add some context for this. So it's a cube that minimizes surface area. All right, hope that's helpful. Please reach out if you have any questions. Again, the whole process is read your situation, come up with what the problem's asking you for an objective equation, find relevant information for a relating equation. Then once you find your objective equation in terms of one variable using that relating equation, h is 100 over w squared, then find a domain, find critical points for your function. Once you get a critical point, give a reason why that either minimum or maximum value happens at that critical point. In this case, we're wanting to minimize surface area. Therefore, we're looking for a local or absolute min to happen here. That means we're looking for our graph to be concave up, and the second derivative verifies that. Second derivative was always positive on our interval, so s of cube root 100 gives us an absolute min. Then answer the question, make sure you list both your dimensions. That's what it was asking for. And then that's it. And then, an added thing was just to say that turns out a cube is what minimizes surface area. All right. Take care. Hope you all are doing well. Bye-bye.